Hey everyone, this is Dr. Walker. This is video 43C called Conservative and Non-Conservative Forces. Hopefully you've noticed in the past few videos that there was something special about the gravitational force and the spring force because both of them acted to reduce the potential energy. We learned that the work done by gravity was negative delta UG, while the work done by the spring force was negative delta U sub S. Both forces wanted to reduce the potential energy of the system. So what is special about those forces is that they are conservative forces. The way a conservative force is defined is that the work done on the particle depends only on the initial and final positions, not on the path taken. So if we consider a block on an incline here, if it goes down this way, or if it goes down this way, the work done by gravity on this object is going to be the same regardless. Does that make sense? Well, think about it. Gravity is a constant force. The work done by gravity is the weight dot the delta R. That means you have to find a component of the weight in the same direction as the displacement. If the displacement is diagonal, but the force is straight down, the Fg is straight down, well, when you take the dot product, you really are going to end up multiplying the Fg by this vertical component of the delta R, which is the delta Y. While over here, if you find the box going straight down, well, it also has the same delta Y. So no matter what path you take, gravity does the same work because it's always finding that vertical displacement. Remember, the work done by gravity, which is the mgy initial minus mgy final, right? It depends on the initial, the y initial, and the y final. It does not depend on the path taken. And then one other thing about the definition of a conservative force is that the work done on the particle moving through an enclosed path is zero. So let's say that, say you have a roller coaster, all right, and a box is moving really fast around, and gravity does work on it as it goes down. Well, as it goes up, what kind of work is gravity doing? If the delta Y is going up, well, the force is still down, right? So the gravity does positive work as it goes down, but gravity does negative work as it goes up, and they end up all canceling out, and the net work is going to be zero. So conservative forces, the most common example are the gravity and the spring. So these are really cool forces because they act to reduce the potential energy of the system. Non-conservative forces, on the other hand, are kind of opposite to conservative forces. The work does depend on the path. Consider friction, for instance. If you move a book from point A to point B, when does friction do more work? For the blue path or the orange path? Well, for the blue path, you've got friction is going to oppose, say kinetic friction is going to oppose the motion, and you're going to add up all of those displacements. But here we have a longer path, so friction, which always opposes the motion, is going to be doing more work. So the work does depend on the path. And so if you have a closed path, the work is not going to be zero. If you move the book all around and put it back to its starting place, well, friction will have done a lot of work, which you probably notice maybe the book is getting a little bit warmer, right? Usually work done by friction is converted to heat, which we also call the internal energy of the system. We'll see that in just a few minutes as well. So the non-conservative forces, they cause change in the mechanical energy of the system. What we mean by this is that instead of energy just being converted from kinetic to potential, there's also going to be a change in internal energy of the system because energy will be lost to the surroundings due to heat. So examples of non-conservative forces would be friction, and air resistance would be some of the most common ones. Let's look at one question. Oh, before we look at the question, the last slide here is, okay, why do we care about conservative versus non-conservative forces? Well, conservative forces have potential energy functions associated with them. What does this mean? So let's just look through the steps here. The work done by a conservative force reduces its potential energy, whether it's gravitational or spring. We've seen this equation before. So the work done by a conservative force can be written here by this integral. We're just making that substitution here. And now if we take the derivative of each side, get rid of the integral, we see that fx equals negative du dx. That means that if you have a conservative force, there is some kind of potential energy associated with it. Now this example here was just for the x direction, but we can generalize. The general form of this is that the conservative force is the gradient of the potential energy function. So these are partial derivatives in the x, y, and z directions. The gradient that you'll see also in physics 2, if you get to that class, we call it the gradient operator, and it's like this. So the force is the gradient operator of the potential energy function. So it's a really, really cool thing that if you have a potential energy, then that means that there is a conservative force that is acting on that system to change that potential energy. So I'm not going to ask you to use this equation for now. I just wanted to introduce it to you because this is a really important result. So just know that it is a fact, but we're not going to actually use this equation for now. Let's look at one question. The person starts from rest with a rope held in a horizontal position and then swings downward. Which of the following force or forces are conservative? Just select all that apply. So we said that gravity was a conservative force, and that's the weight. We said that air resistance was not. What about tension? Is that conservative or non-conservative? So remember that conservative forces have gravitational potential energies associated with them. Tension does not have any kind of energy associated with it. It is a non-conservative force. In this example, the tension is actually, it points away from the object here, away from this person. It always points perpendicular to the motion. So this tension is not even doing any work, and it's not affecting any kind of potential energy of the object either. I just wanted to show you this chart that shows common conservative and non-conservative forces. An additional one that we'll see a lot for the conservative forces is the electric force. We'll see that in physics 2. And then examples of non-conservative force that we've seen are friction, air resistance, tension. Then let's say you have rocket propulsion. You're pushing or pulling something, which usually you'll use a rope or just having that applied force. That's going to be a non-conservative force.